Hi, welcome back. Again, my name is Orlando, and in this video I'm gonna briefly review the Winters method, which is for trend and seasonality corrected exponential smoothing. And we're gonna see how to implement this in R. This method is applicable ideally for a series that have a linear trend as before, but now may have a seasonality to them, which you're going to assume to be multiplicative. So in the book, this is referred to as a mixed model or series, in which the level and trend are sort of additive to each other, but then the seasonality is multiplicative. Okay, so the Winters method attempts now to estimate the level, trend, and seasonality factor at each time, at each period, and use those to make the forecast into the future. Okay, so now we have the same two parameters, initial parameters as before, the initial level and trend, but now we also have as parameters as to the method the initial seasonality factors. So we need to fix P, which is the number of periods per season, and after that we need to specify the initial factors, seasonality factors S1 through SP. And furthermore, now we have the same smoothing constants alpha and beta. So the idea is still to estimate the level and the trend as a weighted sum of previous data points, with older data points having less weight than newer ones. And we also now have a new smoothing constant gamma, which is used for the seasonality factors. So it's the same basic idea. We're going to estimate the seasonality factor is a convex combination of sort of itself and an estimate of it, and gamma will give you that so it will help you construct the weighted sum such that the older data points have less weight than newer ones. Okay, and now finally, the forecasts. So the forecast into the immediate future, into the next period of time, is given like this. So it's we use the estimated level and trend, and you multiply it by the seasonality factor, and on the other hand, the forecast into a possibly longer future. So for L periods of time into the future, the forecast is given like this. So much like the method before with just the trend, linear trend, we're gonna sum the trend estimate L times. So before it was N, now it's L, but it's the same thing. And we're gonna multiply it by the seasonality factor in the corresponding time in the future. Okay, now let's see, in R, again, Professor Pazur gave you some code, so I'm just going to run through it first. And now we're going to use a different data set, which is this data set that reflects the number of births per month in New York City from January 1946 to December 1959. So let's load it. And so this is now this is a numeric vector, so we're going to transform it into a time series, so a TS class. And remember, I told you that the TS class, you can specify the things about the time, basically. So you can, because we know here that the initial time should not be 1, but instead should be the year 1946, the month January, so it's the first month of the year 1946, and we're going to assume that there are 12 periods per year. So the years are sort of the basic unit of time here, and you're going to divide those. So a season is a year, and each year has 12 periods. So the frequency is 12. So we're going to load this, And let's see how this looks like. As you can see, it's the same data, except now it's nicely formatted into the years. And one very nice thing about R is that since 12 usually refers to a division of months of the year, we did not even have to specify that these are months, and R was automatically able to figure out that. So the first period out of 12 probably refers to January, and the second one to February, and so forth. So these are nicely formatted in this way. So that's very good of R. And now let's just plot it to see how it looks like, this data. As you can see here, there is clearly a linear trend like this, and there's also a seasonality. For each year there appears to be some patterns that keep repeating, so these sort of peaks that keep repeating. So we are definitely in good shape to use the Winters method. So let's do that, but first let's decompose this data using this decompose function, which I think is a very nice function, because now let's plot it and see how it looks like. So what it does, it decomposes first you have here your actual time series. It decomposes it into the trend component and the seasonality component. So these two in the middle to get together, those are the systematic component of your time series. And then finally the random component, which is basically what's left. So I think this is a very nice function, because this decomposition can be interpreted in different ways. So you can now clearly distinguish the trend and the seasonality component. And now let's actually apply the Winters method. So we're going to use once again the whole Winters function in R. Now gamma will not be set to false. So we're not going to specify alpha, beta, or gamma. We could, but instead we're going to let the function figure out by its own the optimal values to optimize, to minimize the MSE. We're also not going to, in Professor Pazur's code, we're also not going to specify the initial level or trend. We're going to let the function figure out those as well, the optimal ones. And we're going to run it. Let's see how it looks like. Oh, we're also not going to specify the initial seasonality factors. So all of those are automatically computed by this function, which is very computationally efficient, let's say. And so the optimal alpha, beta, and gamma are here, and the optimal seasonality factors are here. So there are 12, because there are 12 periods in each year, which is the season. So these are all given over here, the optimal ones. We can also plot the result. As you can see here, it's a very decent fit that we have, and we can compute the sum of square errors. And as you can see, it's given by this, and we can inquire about the fitted values, so the values given over here, and the estimate for the level and trend, and for the level, trend, and seasonality, and they are given over here. So the level, trend, and seasonality factor, and these are the basically the forecasts. Okay. Let's get rid of this, and yeah, I think that's it for this part. Now let's briefly just go over the manual implementation that I created for you guys. Let me first comment this. Okay, so much like before, I'm gonna load up the data. The initial estimates for the level and trend, I'm gonna use the same ones as the previous function. So the initial level, I'm gonna put it to be the first data point, so the first demand. So this is not actually a demand in this case, but we're going to keep using demand as, but anyway. And the initial trend, we're going to put it like this. And the seasonality factors, I'm going to use just the optimal values computed before, and the same thing for the alpha, beta, and gamma. So these ones is the seasonality factors, alpha, beta, and gamma. They're actually not necessarily optimal because I'm not using necessarily the same. I'm probably not using the same initial estimate for the level and trend. I'm using probably something different than whatever this function is using. I'm not sure how it's computing it, but it's probably not using the same one. And if we now run this code, so I think the heart of this is this portion, which is really just this, the actual method. So the evolution of, so the estimates of the level are given by this. Again, it's a convex combination of this guy and this guy. Those are here and here. The trend is given by this. The seasonality factors are updated like this. So it's basically all of this is translated into here, and that's how the method is directly given. So let's run it, and let's see what the SSE is for these values of alpha, beta, and gamma, and S, which are the same as before, except for the level and trend, the initial ones. So this should be greater than this guy, which I think it was 91. So yes, obviously it's much greater. So the fit is probably not quite as good. And now let's plot it, and we'll see that it is actually not very good. I mean, it's not too bad, but now, as you can see here, there are some considerable mismatches between the forecasts and the actual value points. So as you can see, I mean, over here in this part, it's kind of corrected, but in the initial, in the beginning, is not quite very good. Okay. So now what we'll do is we'll try to find the optimal values of alpha, beta, and gamma using kind of the same naive method as before, where we define the SSE now as a function of alpha, beta, and gamma, basically replicating the code before, except alpha, beta, and gamma are not specified. They are arguments of this function. So we'll load this, and now we're going to iterate alpha, beta, and gamma over a sequence from 0 to 1, taking steps of 0.05. And we're going to keep track of the current minimum SSE and the corresponding alphas, betas, the corresponding alpha, beta, and gamma. And each time we find a new best SSE, we're going to update it, and we're going to update the alpha, beta, and gamma. So I'm going to run this, and these are the optimal values I can find for alpha, beta, and gamma, and this would be the corresponding SSE, which is not quite as good as the 91 obtained by this function, but it's not too bad. So now let's try to plot this. So this is why I had this comment before with alpha, beta, and gamma, which are these values. So now I'm going to uncomment these and run the same manual code as before, and including this plot, which is what I'm interested in. And as you can see, the fit is much better now. Still not quite as good as when using this function from this package, but it's reasonable enough. So yeah, I hope this was useful, and thank you.